There we go. All right. So for Clara and Anna, gone to Stratford, having a wonderful time while we're here slaving away on physics. What else you want to say?
Tell them to bring us back some Tim Hortons. They're really good in Canada.
Ah, yes. They probably forgot their passports.
Dip slips.
You know, it's real easy to get into Canada, but trying to get back to the United States, that's the hard one.
You get stuck there.
You get stopped. Yeah.
You become a county. Especially
Especially if you like lose your documents or something. Then they like sell your organs or something. Yeah. You're never going back to the United States. Donald Trump is president. There's a wall. Anyways, sorry. The figure shows that there's this like ice in this joint between two rocks, and when the ice expands, it can cause problems, like rock slides and death and destruction. So Block B is directly above the highway. This is number 12, by the way. It's separated from a uphill rock by a large crack called a joint. So yeah, no comments, please. So that only friction between the block and the bedding plane prevents sliding. The mass of the block is big, 1.8 times 10 to the 7 kilograms. So let's see what happens when I put this into draw mode. There we go. And look at that. Okay, so here's our diagram. Basically, I have a big chunk of rock sitting on here, and there's a joint here from the rest of it. So this piece of rock down below is slippable. It can move. And let's see, and there's some forces on it too. It has a mass of 1.8 times 10 to the 7. Kilos. Dip angle, 24 degrees. I gotta be careful. The dip angle is actually this right here, right? No, it is not. Yes, it is. So here's our car. All right. Okay, that's a car. The back end of a car.
It's another rock.
Sitting on the road. It's not another rock, it's a car. And so I'm going to make the claim that that actually does equal this. All right, they're just trying to mess with us, right? Yeah. Okay, so that's 24 degrees, and the coefficient of static friction, 0.63. Sounds good. Show that the block will not slide. Oh, okay. So if we've got mg straight down toward the center of the earth and break it down into two components, we've got mg cosine theta this away, mg sine theta this away, normal force this way, friction, static friction force back this way. So the question is mg sine theta big enough to overcome maximum static friction? Okay, maximum static friction, mu times the normal force, or mu times mg cosine theta. In this case, they are equal. And so we punch in our numbers and get 0.63 times this big number, 1.8 times 10 to the 7. And I'm running out of room fast. Times g. No. Okay, we'll move this out of the way. Oh, look at that. Created room. Cosine of 24 degrees. Okay? Maximum static friction. And then we compare that to mg sine theta. And see, is mg sine theta big enough? And the claim is, by the problem, that it's not big enough. So, you know. Punchy. 1.8 times 10 to the 7 times 9.8 times the sine of 24 degrees yields a whopping, holy moly's, okay. I've got 7.17 times 10 to the 7th. Seems reasonable. That's a big force. But maximum static friction, 0.63 times 1.8 times 10 to the 7 times 9.8 times the cosine of 24. Oh, that's much bigger, right? So scientific notation would be 1.02 times 10 to like the 8th, right? Yep. I should put my calculator into scientific notation mode so it just happens. But yeah. So, on my diagram, what is the static friction force equal to? 7.17 times 10 to the 9, yeah. So this is the maximum static. It can get this high, but right now it's just that, because this guy, this rock here, is sitting on the incline, not accelerating. So we're going to make the assumption that these two forces, mg sine theta and F sub s, are equal. All right. So again, in a multiple choice situation, they try to catch you on that. Okay, it's not equal to the maximum static. It's equal to whatever it takes to balance the forces. All right. Next part. Water seeps into the joint and expands upon freezing. So water gets in there, starts expanding, creating a downward force. Wow. What minimum value of force could trigger the rock slide? All right, so we're going to have some freezing water force. What should we call it? I can't call it FW because that looks like weight. We'll call it F sub ice. F sub I. So how big does F sub I have to get? Take the difference. All right, we know what kind of maximum static friction we're looking at. So it looks like the difference between the two numbers we just calculated should do it. Okay, so take it away. You finish this off. So the problem with number 12 was there's a lot of complication in there, right? There's a lot of added detail that just makes it look different than a block on a ramp. But that's really all it is, a block on a ramp. All right. Any others in this set we ought to look at?
What was the final answer?
I don't know. I just had it up there. What do you mean, what's the final answer?
I know, that's fine. I knew you had it.
All right, let's see. If I do this, oh, look at that. Technology is amazing when it works. So the claim is 3.0 times 10 to the 7 newtons, which kind of makes sense. We had like 7 times 10 to the 7 and 10 times 10 to the 8, and, or 1 times 10 to the 8, so 10 times 10 to the 7. Take the difference and you get about 3.
Makes sense.
Yeah. So about 30 meganewtons.
It's a lot of ice.
It's a lot of force. Doesn't take much ice to create a lot of force. That stuff expands and those little molecules just have to do what they do.
Really?
Yep.
If you put ice in like a concrete block and fill it all the way up and froze it, would it break the concrete?
It actually would.
Factor ovens, right?
Yeah.
Water gets in them.
Yeah. The roads are porous enough and
Hey,
Good
I
morning.
left my Chromebook in here yesterday.
yeah, you did. I was wondering whose Chromebook that was. I went to unplug my coffee pot and I said, no, I'm unplugging someone's Chromebook.
She gets lost easily.
Yeah, she does.
I just realized because I needed it for first hour. And then
Yeah. Well, I'm glad you got it.
Thank you. Sorry for interrupting your class.
Not a problem.
So,
It's kind of a big deal.
Have fun, guys.
Kind of a big deal. My physics teacher back in the day actually I'm not sure why he did it, but he took, he found this cast iron ball, this hollow cast iron ball. He puts water in it, and then he screws the top. It had an opening that kind of screwed in, so he screws it like with, big wrench, and then he puts it in a trash can, and then he pours like Freon and liquid nitrogen into the trash can, and it freezes the water. I remember this demo very clearly.
It's like,
And then there was this big boom, and the water actually rips open this cast iron ball, and he pulls it out, and the water crystals are all teeny tiny little water. It looks like a bunch of diamonds, and this thing is basically broken in half, even though it's made out of cast iron, like
you
a
should
half
do
inch
that
thick.
demo.
I should do that demo.
This
I don't know
is-
where he got the materials. I
Yeah,
think
where
he
do you
knew
find a
somebody.
cast iron ball?
Yeah, where do you find a hollow cast iron ball that closes with a screw?
I can lend you mine, but I mean, it's.
Well, but then it'll be ruined.
Yeah, exactly.
So I need one that you don't want anymore.
Alright.
Okay. But anyways, yeah, the power of expanding water is amazing, or the force of expanding water. I shouldn't say that. I'm a physics teacher. I should use the right words. Okay. Next one. The trough question, number 69. Okay, let's take a look at it. All right. So I'm going to take this one out for all posterity. There we go. The trough question. I'm not sure I could even draw what they drew here, but we've got this like in a right angled trough, and there's a box in it sitting in there like so. That's a really bad diagram. Oh, that's one of my worst diagrams ever. Okay, so you can't even tell what that is. But Claire and Anna, look on page 136 at the bottom right-hand column, and you'll see what I attempted to draw right there. Now, we'd like to know what's the acceleration of the crate going down this right-angle trough. If we know what the coefficient of static friction is, we know mu sub s, we know theta, and we know g. So those are our unknowns. Mu sub s, theta, and g. Now, there's always one or two questions like this on the AP test where they don't give you any numbers. They just say, write the answer in terms of those variables. Now, I find it a lot easier to draw this like so. So, with your indulgence, I'm going to erase this terrible diagram. Actually, I want, uh-oh, I just messed up. I want to stay in drawing mode. There it goes. Whoa, that was scary. It came back for just a second. Shades of the thing that happened before, which I won't talk about. Was this the class
Yeah.
where I had the weird symbol on the board that wouldn't erase?
Yeah.
Okay. All right. So, what I'm going to do is look at it from the side. Okay, so here's our trough, and here's the box sitting in the trough. And then the front view looks like this. If if this thing's coming down, it's going to hit you in the face. Here's the front view situation. Okay. Now, we've got weight here, mg. We've got some kind of frictional forces from the sides of this thing. I'm going to just draw one of them because it's kind of hard. I could draw both, but we're going to call this kinetic friction, right? We're looking at the acceleration of this. Yep. So normal force, also, it's going to be weird. Okay, we got a couple of normal forces that are going to be shooting out here from these two surfaces. And then, of course, we've got, that's it. We're going to break mg down into two components, and we're going to have mg cosine theta, mg sine theta. All right? So this diagram, this front-facing diagram, mg sine theta is coming right out at your face. Okay? This mg cosine theta would be straight down, okay? But the normal forces are doing this. Okay, so it's kind of like you got a pair of ramps that you're sliding down against. And the question is, how big are those normal forces? You're going to love this. What I got to do is take that mg cosine theta and break it down into components. Don't look at me like that. I'm going to take mg cosine theta and break it down further into two components, one this way and one this way. So this is 45 degrees because this is a 90-degree thingy. So this is mg cosine theta cosine of 45 degrees, or sine of 45 degrees, it doesn't matter. And this other guy is exactly the same. Now, in a right triangle situation, 1 square root of 2, right? If this is 45 degrees. So that means the sine of 45 degrees is 1 over the square root of 2. So with your permission, I'm not going to say cosine of 45 degrees because that's just weird. Taking the component twice, I'm going to divide by the square root of 2. I'm going to multiply it by the sine or cosine of 45 degrees, which is the same. So I'm going to do mg cosine theta over the square root of 2 over here. So we've got this pair of normal forces, and we really have a pair of frictional forces. It's just kind of hard to draw on this, you know. We've got like these normal forces that are, 90 degrees apart. We've got frictional forces, oops, this is a K, that are identical and pointing back along those two sides. And we would like to figure out, okay, the acceleration of this thing. How you doing, Mr. Trammell?
This is a lot. Like, I would have never known to done
Yes.
this.
Well,
So I'm just worried when I get to the final exam. Like, I know
Oh,
we're
don't-
there's tons of problems.
Don't worry
but
about
still,
the final exam yet.
I'm still worried. Like, I feel like there's so many problems that I just would never ever have thought.
Josh, calm down, dude.
Yeah. Okay, Josh, how old are you right now?
I am 17.
Okay, are you worried about your retirement plan?
Yes. I mean, I
Dang
haven't
it.
started in my 401k.
Okay, so I was, can you use
I
that
have
as an
to say-
analogy that, it's way far off, so don't worry about it. Same with the exam, okay, just hang on.
I already said it.
This one is just especially evil.
Okay.
But, here we go. We're gonna apply F equals ma to it. That was magical, wasn't it? And so I've got these two frictional forces back this way in mg. So I'm going to say mg sine theta minus these two frictional forces along each of these sides here. So I'm going to put a 2 up front. Equals ma. Now, of course, frictional force, kinetic friction, is mu times the normal force. And that's where these mg cosine thetas over 2 square root of 2's come in, because these two normal forces are equal to that. So the hardest part about this is that stupid square root of 2. Everything else here is pretty, makes sense. But when you take the component of a component, that's when my brain starts to melt too, okay? So, and I've been at this a while. So I'm going to write mg sine theta minus 2 times mg cosine, oh, I need mu. Ah, dang it. Some days. Let's see, I want small eraser. Ooh. Oh, that's not what I wanted to do.
That's pretty cool.
Okay. Back to work.
In the video, you should act like you were writing that. You should let me just rewrite it out.
Yeah. They think I'm really smart.
You're like, oh my gosh.
All right, so 2 mu sub k times this mg cosine theta over the square root of 2 thing, which was slightly evil, equals ma. Okay, So after you write that equation, what's the first thing you're going to do?
Get rid of that.
Get rid of the m's. I thought you were going to say something else like, you know, get sick. No, you're going to go, wow. Okay? Now, we can also, like, if you take a look at the answer in the back, they pulled out the g. So we've got sine of theta minus, now we got a square root of 2 on the bottom. So let me just switch colors here so you can see. I wouldn't bother with it too much, but if you were like Mrs. Triesenberg, you'd say, oh, I got to get rid of this square root of 2 business. So I'll multiply the top and bottom by the square root of 2. And square root of 2 times the square root of 2 on the bottom is 2. So this will cancel out. So they just tidied it up a little bit, and it's, you know, a little irritating, but they made the answer very pretty that way. And so I've got the square root of 2 times mu sub k times the cosine of theta equals a. So I hope that's what they had. I think that's pretty close to what was in the solution. How you doing out there? Did that help?
Yeah.
Yeah. Yeah, you're right though, Mr. Schmel. This is beyond the pale. Taking this mg cosine theta and having to break it down into components. Once you've taken mg and broke it into components, and then you take a component of it and break it up into components, that's when, you know, who would have ever thought of that? Yeah, so kind of a crazy problem. All right. How are we doing on time? Very good. So, that's what. So, how's the lab going? He asked. It's going? Okay. The reason I asked, let's see. Yeah. Because the reason I asked is today in my plans, I have, let's take a look at drag force. So I'm actually going to like give you the answer, where I try not to give you the answer while you're doing the lab. Try to make you, you know, come up with it yourself. Come on. There we go. But the other day, come on, go away. There we go. So this would be like Roman numeral 4 or something like this. Okay? They don't call it air resistance, they call it drag force because it could be like water resistance. If you're a torpedo going through the water, you experience a similar kind of drag that you do when you go through air. It's just different fluid. So you told me the other day what the things are that will affect drag force. Okay, you stick your hand out the window, stick the ball out the window as you're driving down the road. What were those things that affect the drag force? You said? Yeah, it's like cross-sectional area.
Yeah.
It's kind of the silhouette of the object. How much area does it present to the wind? So if you put your hand out flat against the wind, there's more resistance than if you turn your hand 90 degrees and, you know, let it slide through the wind. If you're a skydiver and you want to slow down, you don't have your chute open yet, you go spread eagle and let the wind just, or the air, just pound at your whole body. You know, you increase your cross-sectional area. If you want to go fast, you know, you go feet first or head first and pull your arms in and just, you know, shoot like an arrow. You can go faster and slower by using the air. All right, cross-sectional area, we'll just use A for that. What else was there?
Amount of oxygen in the air.
Yeah, the density of the fluid you're going through.
Yeah.
Okay. using the Greek letter rho. Stop using D because D gets confused with distance and a bunch of other stuff. So they stick with rho. And what else? Speed, velocity, you got it. And one other thing, if you've got a ball that you stick out the window, or you have a disc which has the same cross-sectional area as the ball, there will be a difference in the amount of drag force. The ball is smoother. The air goes over the top and bottom of it very nicely. So you have this situation. It's called laminar flow. So balls, spheres, are really kind of aerodynamic. But something with the same cross-sectional area, say this is a round disc as seen from the side, yeah, not so much. I mean, this is going to be bad news. There's going to be turbulence back here and all kinds of horrible stuff happening. And there's going to be a lot more drag on that shape than this shape. Even though they have the same cross-sectional area, they're moving at the same speed, they're moving through the same fluid. So we've got this thing called coefficient of drag that takes all that into account. Drag coefficient. And use capital C for that. All right, so the drag force equation is just multiply all this crap together. So it actually has a 1/2 out front. I don't know why they did that, but it changes the coefficient of drag. So there's a 1/2 front out front. There's the coefficient of drag. There's the density of the fluid. There's the cross-sectional area, and then there's the velocity. So our hope was that when you do a power law fit on this curve, that you say, oh, look, it's v squared. We talked about graphical analysis yesterday, did we? Use graphical analysis instead of Plotly? Didn't mention it? Okay. So if you use Plotly for this, you're going to, you're going to get a curve, not a straight line. So how are you going to fit it? How can you tell that the relationship is v or v squared or v cubed or v to the fourth or whatever? With Plotly, the only thing you can do, your only option is a polynomial or a quadratic. And it'll fit, and you go, oh, look, it's quadratic. But how do you know it's quadratic? Maybe x to the third or x to the fourth. Maybe a quintic works better. Sometimes you want the option of power law. So one suggestion for the lab when you're putting it together is download an app called Graphical Analysis. It just became available. That's why we didn't do it first. I would have started off the year with it, but and I tested it over the summer and it worked great. And then September 4th, they did an update. And then suddenly nothing was working. And what was happening was our version of Chrome that we use on our Chromebooks was not catching up to Verniers, the company's version of Chrome. And so when we caught up to them, now suddenly we can get graphical analysis. And if you go to the Google App Store, the Chrome Store, and you get graphical analysis, you just search for it. If it doesn't come up, it might be that your Chromebook is not yet compatible, and just restart your Chromebook. Or there's actually like a little icon at the bottom somewhere in your Chromebook that says, update your version of Chrome, and it will update. Once it's updated and you restart your Chromebook, then go to the Chrome store and graphical analysis will be there. But graphical analysis is really slick, and one of the reasons we're going to use it more often is it does have a power law option. And what it'll do is it'll try to fit your graph to y equals some constant times x to the b. So in our case, y is going to be drag force. A is going to be like all this stuff, 1/2 c rho A sitting out front. And B is what we're after. Okay, so I've got some groups showed me, they did it in graphical analysis, and they got like 1.8. And I'm saying, ooh, that's not bad. nature generally doesn't do powers of 1.8 or 0.285 or something like that. When you look at the equations of physics, it's generally to powers of 1, 2, 3, 4, or powers of 0.5 because it's the square root. So hopefully B turns out to be something close to 2. We'll see. Now, this is inexact science. There's a lot of chaotic things happening here when you're dealing with drag. There's some texts that will tell you as the velocity gets larger, this exponent actually changes. So if you go fast enough, you drive your car half the speed of sound or something like that. I saw Trammell try to do that on the way to school one day because he was late. That actually this exponent can go to 3. The nature of the air itself changes and how it interacts with your car. So, all right. So I've got an example using this thing. Then I'll assign a bunch of problems. And then, next week we'll do circular motion, review, and test. So we're looking at a test Wednesday. We'll see how that works out. I'm going to be gone on Wednesday. I have to be at the Capitol. We have a robotics presentation in the rotunda of the Capitol building in Lansing. So I'm going to be really important for one day. Well, not so important. The students will be important.
You important every day, so.
That got recorded too. I got to move the microphone over so that, nice things like that can be recorded. But we may even rub elbows with the governor. We'll see. So the tough nerd might come out and look at our robots, which would be kind of cool. That would be kind of impressive if we could get that. All right, anyways, I'm going to erase everything here and go back to my PowerPoint mode here. Come on. Okay. And of course, it's the wrong PowerPoint. These are the answers. I don't want the answers. Let go of my computer, you thing. There we go. So, yeah, we'll do the puppy later. You wanted to do the puppy today, didn't you? We'll do the puppy. We'll see if we have time. Hey, don't make fun of me. Okay, the question is, what is the terminal velocity of a 2.75 gram ping pong ball? It's got a radius of 2 centimeters, and its drag coefficient is 0.441, and we'll assume the density of the air is a kind of a common 1.2 kilograms per cubic meter. So a ping pong ball, switch to drawing mode here, reaches terminal velocity when its downward weight force equals the upward drag force. You know that already because we did it with the silly coffee filter lab. And so we want to know what that velocity is. So what you gonna do? What? Take mg. Find mg. All right. So what if we say that since we know these two are equal, we replace FD with 1/2 C rho A V squared thingy, and see if we've got enough stuff to figure out what V is. You don't look happy, Mr. Trammell.
I just did the first one, and I just got FD, and then I went from there, which is, it's either way. And then
You already solved this problem?
I thought I did, but I'll see what's doing.
That's awesome. Okay. So you're right, we do have M, and we have G, and we have C, and we have rho. We don't have A, though. The Philistines didn't give us A. But we do know that this thing has a radius of 0.020 meters. Therefore, cross-sectional area, pi r squared, is going to be something small, because it's a ping pong ball, for goodness sakes. So pi times 0.020 squared gives us this tiny area of 0.00126. Square meters. And now we're cooking with gas, right? So we're going to say, okay, V is equal to the square root of 2mg all over C rho A. So it becomes a pretty trivial problem at this point because we know all these numbers. We stick them in and we can theoretically compute the terminal velocity of this ping pong ball. So be sure to turn mass into kilograms, 0.00275 I believe. Oh, wait, Emily, being stupid again. There we go. Oh, I was stupid again. I just killed everything off. Hang on. Back to drawing mode. And this is kilograms. And this is 9.80 meters per second squared. And down below, we've got drag coefficient of 0.441. A fluid density of 1.2 kilograms per cubic meter. And we've got this cross-sectional area of 0.00126. So this is not hard, except keeping track of everything. Making sure they're all in the right units. And we're good to go. Okay, take the square root of the whole mess. Are you getting like 9 meters per second?
Yep.
That's still pretty fast for a ping pong ball. It's still smart if it whacked you, right? So 2 sig figs, I guess we are stuck with 9.0 because it's like 8.9908 or something. Okay. So I think that's a little fast, but it's probably the drag coefficient that's, you know, a little iffy. So 9.0 meters per second for terminal velocity. Sometimes they put a little t there, you know, just to indicate, oh, it's terminal. Okay. How y'all doing? This is first hour, so we still have like 12 minutes to go. I think it's time for the puppy. All right, so here we go. We're gonna lose all this. Bam. Gonna switch back to regular mode and find the puppy. Let go of my computer. Sound like happy little kids out there. The puppy, oh, we like the puppy. All right, here we go. So, this is a drawing that I created myself. I did not steal this from a book or anything. Can you tell?
You drew it?
Yep, that was me.
Is that its tail? Or is that another foot?
Okay, the hungry puppy notices that his food and dish together have a mass of 2 kilograms, is sitting on a table out of his reach. However, a rope is attached to the dish and threaded over a frictionless pulley. The puppy jumps up and grabs the rope in his mouth. The dish of food accelerates at 5.90 meters per second squared, and the coefficient of friction between the dish and the table is 0.320. Find the mass of the puppy. So he jumps up, grabs the rope, and by the behavior of the dish and the puppy, you can calculate his mass. How's that for cool? Liz is just, overwhelmed with joy at this problem, I can tell.
Yeah.
All right. You may assume that the puppy is a Siberian Husky puppy. How's that for a hint? And yes, that's its tail. This is supposed to be a tail. See, that's his mouth and eyes, the little ear. He looks like a dingo. A dingo is stealing our dog food. All right, so go to it. Meanwhile, I'm going to make preparations. Okay, and while you're working, I got the assignment up there for Monday. Please do the Chapter 6 problems, 16, 20, 25, 38, and 39. And the last two, 38 and 39, deal with air resistance, drag force. So 16, 20, 25, 38, and 39. All right. How's puppy problem going?
It's going rough.
Well, oh, you're good. All right. All right. So there's two forces on the system. Do the Siberian Husky approach. We've got dish and dog and rope being one system with two forces acting on it. And you can still draw the forces on the dish that are, both down. So I've got the food times G, mass of food times G, and we've got normal force this way. So if you write the equation of motion, you got mass of dog times G minus the friction force equals ma. And we need the total mass being accelerated in. All right. So the physics is over. Well, we still have to replace f sub k. The physics is almost over. So mdg minus mu times mfg, careful, equals mass of food plus mass of dog times A. All right. Do we have enough to solve the problem? We know the food in dish, 2 kilograms. So that's m sub f. We know the acceleration. We know the coefficient of kinetic friction. I think we've got this thing solved almost, right? Now it's a matter of making the algebra work for us. So mdg minus mu m sub fg equals m sub fa plus m sub dA. Take everything with m sub d and put it on one side, put everything else on the other, and let's have it. So over on this side, I'm going to have m sub d a minus g. Okay, all I did was take m sub d and subtract it from both sides and factor out the m. This m sub fa I'm going to slide over this side. So I'm going to have like a negative m sub fa minus mu m sub fg. All right, I feel like I did something wrong. Looks okay though. I don't think I did anything too silly besides get out of bed this morning. Because a minus g will be a negative number. That will take care of our negative signs. All right, so I'm kind of running out of room. Sorry, Claire and Anna. So I could say on this side, I've got m sub f a plus g, a plus mu g. So I multiply this side by a negative 1 as well. And if I multiply this side by a negative 1, it becomes m sub d g minus a. That just makes me feel happier. And then if we divide both sides by g minus a, we did it. We got the mass of the puppy. Woohoo! How you doing out there? So the physics is f equals ma, the next line, where you take m sub dg minus f of k equals ma. And then the next line where you replace f sub k with mu m sub fg. And then the physics is over, and it's a whole lot of crazy algebra to solve for m sub d. But we can do it. We know everything there except for the mass of the dog. All right? That's why in this class I asked you to have a prereq of calculus, because if you're in calculus, you can probably handle crazy math. When the algebra starts getting ropey, you don't give up. You keep moving. We really don't need a whole lot of calculus until end of first semester, beginning of second semester, but you're used to kind of things getting kind of crazy. All right, so that's it for today. If you want to know the numerical answers, slide the numbers in, but we solved it. So those problems for Monday, the drag ones aren't too bad, but give me a call if you run into some difficulties. And I'm going to shut down this recording here before I embarrass myself some more.